Not sure if this microphone is working. It's not. Okay, this microphone is unfortunately not working. All right, great. Thanks so much to coming to the second part of today's seminar. So I'm delighted to introduce our speaker, Robert Huang. So Robert completed his undergrad at National University of Taiwan, and he's currently a grad student finishing up his PhD at Caltech, advised by John Preskill and Tamada Dick, and he's done a lot of wonderful work on kind of the general area of quantum learning theory, how to learn various properties of quantum states very efficiently with randomized and non-randomized constructions, with or without quantum memory. Yeah, so a lot of really fun stuff. And he'll be talking to us today about a theory of learning in the quantum universe. Take it away.
Yeah, thank you so much for the introduction. So since the microphone might not be working, I'll try to speak as loud as I can. The topic of today's talk would be theory of learning in the quantum universe. I would be talking about a lot of recent progress with me and my collaborators, including Richard Kuhn, Giacomo Torelli, Victor Alba, John Preskill, Sid Hunchen, Jordan Cutler, Jerry Lee, Michael Broughton, Jerry McLean, and many other wonderful people from many different organizations. And yeah, let's get started. So I'd like to motivate sort of the research that we're doing by just noting that a very big central goal of science is to learn how our universe operates from the microscopic scale to the astronomical scale. And since our universe is inherently quantum mechanical, if we can gain the ability to efficiently learn in the quantum world, then it could potentially lead to many different advances. For example, if we can, by learning from experiments, create a powerful predictive model that allows us to predict what this blob of quantum particles have certain properties and so on, it could potentially lead to advancements in designing new catalysts, designing new drugs and so on. And if we can efficiently extract interesting topological properties of quantum many-body system, that can also allow us to gain new insights into exotic quantum matter, and the ability to learn, say, intrinsic properties of some quantum devices could also help us engineer better systems for computing, for communication, and for sensing. So as a result, in order to accelerate and automate the development of science, in particular science related to quantum physics, it is very important to understand how we can design better algorithms to learn in the quantum universe. So what I mean by that is there are some quantum objects, say it's a quantum state, it's some quantum dynamics, it's a quantum device that you have engineered, it's some big quantum many-body system, or even it's the phase diagram and so on. So there's some unknown object that's related to quantum things and you wanted to learn about it. There's just some unknown aspects about it and you wanted to better understand it. So that's essentially what we mean by learning. And more precisely, I'm going to consider learning in this task as a more broader information processing capability. It's not just training, say, convolutional neural network to classify cats and dogs, but sort of a sequence of actions that allows us to actually learn about some unknown aspect. In particular, this would include first receiving information about some unknown aspects of the universe that we wanted to learn. And that could be done by doing experiments, by performing measurements, and so on. And after that, after getting these information, we would like to process it to create some predictive models. We store that predictive models in a memory, such that subsequently we can use this predictive models to predict situations that we have never encountered before. So that's going to be the sort of the broader learning definitions that we're going to utilize. And in today's talk, the overarching question that we would like to understand is in what kind of situation and what kind of algorithm should we use to efficiently learn in the quantum world. And this would be separated into two parts. The first part of the talk, I would focus on learning using a classical machine. And the second part would be about learning using a quantum machine. The first part would take around like 2/3 of the talk, and the second part would be like around 1/3 of the talk. And let's begin with the first part. So basically, we have some classical machine learning models, or more broadly, just some classical computer that's trying to learn about some aspects of the quantum universe. And there are two key questions that we would like to understand. The first one is, what can a classical machines learn about some complex quantum systems, and can classical machines that can learn perform tasks or solve certain problems more efficiently than algorithms that cannot learn. These are the two main questions that we're going to try to address and provide some recent progress in addressing these questions. In particular, I'm going to talk about a wide range of works done by me and my collaborators. In the first part of the talk, I will be focusing on these papers. In particular, I would start with the first one, predicting many properties of a quantum system from very few measurement, which is a paper that me, Richard Kuhn, and John Praskol put out 2 years ago on published at Nature Physics. And this is going to form sort of the foundation of everything we're going to talk about today. So I would like to start with that. I think some of the more hardcore quantum information theory people probably already heard about classical shadow for quite a lot of times, but since I guess there's people outside our field, I would like to present a sort of a brief review on what we try to do in this paper. So this paper proposes this framework called the classical shadow framework. And the big question that the motivating question we're trying to address in this framework is to understand how can classical machines see quantum many-body systems. And what we mean by seeing is essentially the ability to convert a quantum system, so some unknown quantum system that we have created in the lab, or that just happens in nature. We wanted to turn that quantum system into some classical representation such that we can utilize this classical representation to predict many properties of the quantum system. So that's what we mean by the ability to see. So why do we want to have such a ability? Why do we want to construct classical representation of quantum systems? There are two main reasons. The first one is more fundamental. Essentially, when we have created some quantum system, we would like to know what this system is. But since humans, as we are a classical being living in the classical world, in order to be able to understand quantum system, we have to turn it into some classical representation. So the first one is more of a fundamental kind of aspect. But on the more practical aspects, there are many proposals for using quantum devices. There's many quantum applications that actually require an interface between the classical and the quantum realm. So you would have the classical computer that try to control a quantum device to do certain things. And in order for the classical computers to do a good job in controlling the quantum device, such as in a variational algorithm, you would like to have the classical algorithm be able to understand what this quantum system is. What is the quantum system is actually doing right now? What is it generating right now? And using that information to improve upon it. So the standard approach for constructing classical representation of quantum states is known as quantum state tomography, where you just try to learn the complete representation. So say we focus on qubit system, so you have an n-qubit quantum state, and now you wanted to learn a complete representation, that would just be an exponentially large matrix. And since this is an exponentially large matrix, even the optimal protocol, such as one proposed by Hawk L. and Ryan O'Donnell and John Wright, requires an exponential amount of resource in all kinds of aspects. It needs an exponential number of copies. It needs an exponentially large quantum computer to store all these copies and process it. And after that, the representation that it generated would also scale exponentially large because you're trying to store an exponentially large matrix. So in order to circumvent this exponential scaling, in this paper, predicting many properties of a quantum system, we propose this classical shadow framework based on this idea, and also to better understand it. So there are some more heuristical way of trying to create representation of quantum systems, such as using neural network, using tensor networks, but they're more limited because they can only represent things that are within the class. For example, if you use MPS, it can only represent things with limited bound dimension, and it's in 1D and so on. So for classical shadow formalism, we wanted to create a more general tool for learning classical representation of an arbitrary quantum state. In particular, in this paper, we proved the following theorem. We showed that there exists a procedure, which is a pretty simple procedure that's experimentally feasible and has already been implemented in various physical experiments that guarantees the following. So given three hyperparameters, B, M, and epsilon, this procedure can learn a classical representation of an arbitrary unknown quantum state rho by performing a number of measurements that scales as v log m over epsilon squared. And the guarantee is that after you have learned this classical representation, given any observables, m observables, O1 to Om, with a norm bounded by b, the procedure can utilize this classical representation, which is also known as the classical shadow representation, to predict the expectation value of all of these observables up to epsilon error. So basically, m is the number of observables you wanted to predict, b is the norm. Think of it as how large this observable takes value, and epsilon is the prediction error. So for example, if you wanted to predict 10 to the 6 different observables, each of which has the norm bounded by 1, naively what one would do is just, given a copy, measure first observable, and then do that repeatedly for 1 over epsilon squared times, just average over it. So now you get the expectation value for the first observable. But now, since everything collapsed due to the measurements, in the second observable, you would do that again. So if you have 10 to the 6 different observable, the number of measurements you require would scale as 10 to the 6 over epsilon squared. However, this theorem shows something surprising. It says we only need 6 log 10 over epsilon squared measurement in order to capture all these 10 to the 6 different properties. And furthermore, when we are doing this, like according to the theorem statement, there's 2 parts. In the first part, when we're doing the measurement, we actually don't know what the property we wanted to predict. We don't really need to know it in advance. Creating this classical representation, subsequently, you can just use it to predict all of these observables up to epsilon error with high probability. So now I would like to showcase or present a more look into what this procedure is actually doing. So the procedure.
Assuming anything but locality.
That's a great question. So it actually depend. Like there's a freedom in the procedure that actually changes the norm. So depending on what kind of maybe it will become a little bit clearer after I explain the procedure, and I'll come back to this question. So the procedure here is the following. So there's 2 steps. The first step is a data acquisition phase. Each time when you do a measurement, we perform the following. We sample a random unitary to rotate the system, to hopefully scramble it, and then measure the system in a computational basis. So by doing that, we will obtain a classical bit stream. And after that, what we would do is we would store what we call the classical shadow. So this is a state, Si, that's equal to the inversion of the original unitary you apply, so followed by the applying onto the bit streams that you get. You can think of it as you're first rotating it, measure, and now in order to capture the original system, you should rotate it back. So that's the purpose of this UI dagger. You don't really store the state, Si. You just store the bit string, which is a classical bits, and the description for UI. So some description that tell you what this unitary you have sampled. So you can sample it from different kinds of unitary ensemble. You can sample it from, say, short time quantum evolution. You can sample it from tensor product of single qubit gates. You can sample it from a deeper circuit, like a more longer time evolution. You can sample it from different ensemble. And basically, the ensemble that you sample from would affect this norm that I mentioned in the theorem statement. So for example, if you sample it from, say, a short time evolution, then the corresponding norm would scale with the locality, meaning that you will be able to predict a large number of local observables. But if you choose the unitary to be, say, long time chaotic evolution, then the corresponding norm would associate it to Frobenius norm. And in that case, locality doesn't come into play, and you can predict highly non-local things. So so that's like one step, and you just keep repeating it. So intuitively, you can think of it as you have a high-dimensional system, your quantum system, it's exponentially high-dimensional. And every time when you're doing this experiments, you're just taking random direction and looking at it, and you're casting this kind of classical representation, like classical shadow of this state, and then you just keep repeating it. And now using this collection of classical shadow, you can make prediction about this unknown state. So during the prediction phase, what one should do is the following. So you're given this S1 to ST, the collection of experimental outcome you obtain from the experiments. How do you predict property? Essentially, we're going to use this identity, the label by the star, which is one could show that the expectation value of these classical shadow SI would be equal to applying some CPTV map to your unknown state role. And in various situations, when you apply a random unitary that's sufficiently random, then this M will be invertible. And when it's invertible, you can just immediately get the following identity, which says when you create this M inverse apply onto SI, that object will be equal to the unknown state rho in expectation value. So what you can do is you can just, every time you see rho, you just replace it by that form. And you can just utilize that to make prediction. Of course, there will be random fluctuation because it's only equal up to expectation value. But when you have these t different things and you do a proper statistical procedure, you can make prediction accurately. So in particular, in the paper, we present this median of mean estimation where you just compute trace of O, replacing rho by this M inverse thing. And then you take the average for different chunks, and then you take the median. So taking the median makes everything much more robust, and you can essentially get the theorem that I previously mentioned. Is there a question?
Yeah. So just to confirm, so in order to do this, we will need to really describe the state SI because SI is obtained by random unitary applied on a computational basis. So it seems like itself is mentally hard to write down.
Ah, I see. Yeah. So actually, in the original paper, we focus on random unitary that are Clifford. So in that case, then everything can be done very efficiently classically. But I think there's also various follow-up works that try to look at when this random unitary is some like short time evolution, that's just a quantum dynamics, and try to understand how can one utilize like tensor network techniques and combine with classical shuttle in order to make prediction.
So in general, in order for this method to be useful, you want an SI that can be described in a polynomial.
Yes.
Yeah.
So you don't want to first, just from an experimental practicality, you don't want to apply this unitary UI to be really hard random. You want it to have some small description. And then in that case, SI, at least you can describe it efficiently. But then you also want to be able to calculate these things, trace of O, M inverse SI in a efficient classical manner. So yeah, so using this formalism, we found that you can predict a wide range of different properties from many fidelities with your ideal state, entanglement witness, entanglement entropy, two-point correlation function, etc. So in the paper, we've also showcased sort of its empirical performances and its practical use. And after the publishing of this work, there has been a wide range of different follow-up that tries to improve upon it, like, for example, generalize it to fermionic system, to bosonic systems. And me and my collaborators have also been improving upon it. For example, in this related work, efficient estimation of Pauli observable by de-randomization, we showed that you can utilize this theoretical computer science technique called de-randomization to remove the randomness in the random unitary that we are applying. And by doing this de-randomization, you actually get a significantly improved performance for prediction accuracy, which is quite surprising. And in collaboration with Peter Zoller and Ronald Bloss group, we've also shown that you can utilize this framework to certify entanglement in mixed states. And with collaboration with Suwon Choi and other experimentalists at Caltech, we also showed that you can replace this random unitary that I talked about by a chaotic quantum evolution, and you can still get a lot of similar behaviors when you make that modification. And that was shown in this last work on emergent randomness and benchmarking. So now, after talking about this framework for representing quantum states using this classical shadow representation, we're going to build upon it and try to answer even more challenging questions. And that's essentially done by these two papers. Particularly the question we...
Before you move on,
Yes.
in your estimator, you have median.
Yes.
Comment with what's the source of the broad distribution? Presumably that's why you use median rather than.
Yeah, so the problem is actually the following. So it arises when you say, like, wanted to estimate like this global property where you apply like deeper time evolution. What we do is we utilize, say, a Clifford circuit. So it's only mimicking a hard random evolution. And when you try to do that, when you try to mimic it, it's not, it only mimics it up to the third moment, essentially, from a statistical point of view. And if you only mimic up to third moments, it means that there's going to be quite some probability where it might not mimic it properly and produce some kind of bad results. And this medium essentially throw away those things. It's still quite rare, but that could happen. And by taking medium, it allows maybe among these K chunks, one of it will be corrupted. So now when you take the medium, it will be correct. So that's sort of the purpose for having this medium. But for some other random unitary, actually, we don't need it. So it depends on the situation. Yeah, so now I'm moving on into trying to utilize this classical shadow technology in order to do something even fancier. In particular, we would try to understand if utilizing these ideas that one can create representation for any quantum states, can we then develop classical machine learning algorithms that can learn to solve challenging problems in quantum physics and hopefully yield better solutions than non-machine learning algorithms. In particular, in this work, we focus on the task of predicting ground states. This is a very fundamental problem in physics. And more precisely, we have some high-dimensional vector x that describes some n-qubit Hamiltonian h of x. So you can think of the vector x to specify, say, the laser intensity or some knobs that the experimentalist could control that would create a different Hamiltonian acting on the system. And the goal is, given this parameter x, which is a high-dimensional vector, we wanted to predict the ground state representation for this Hamiltonian h of x. In particular, this classical representation could be a tensor network, but since we don't really know if tensor network can describe any, say, 2D or 3D systems, I don't think there's a formal proof of that yet for the ground state. We were going to utilize classical shadow formalism since it works for any quantum system. So this kind of questions arises in many sort of fundamental physics, like in quantum mechanics 101, we would solve the ground state for this oscillator, but also for more practical purposes, like in understanding properties of molecules and so on. We would like to first understand its ground state properties. However, this problem is known to be extremely hard. So complexity theorists would come and tell you that you cannot really solve this problem. This is too hard. In particular, this is even hard when you restrict this significance. Say you only care about a two-dimensional system. So it's a geometrically local Hamiltonian living on a 2D lattice, and say it has a spectral gap of 1, and the machine doesn't really need to create the ground state representation. All it has to do is to predict a one-body observables in the ground state. And furthermore, we only care about average prediction error. So the machine doesn't need to be able to predict it for any x. It just needs to predict it for most of the parameter x. Then we can show the following proposition using standard results in complexity theory. Essentially, if we assume NP-complete problems cannot be solved in randomized polynomial time, which I think most people would believe, then no randomized classical algorithm can achieve a prediction error less than equal to 1/4 within polynomial time. So it basically states that if you assume that NP-complete problems cannot be solved efficiently, then you cannot get a prediction error of less than equal to 1/4 efficiently using a classical algorithm. So this is a very hard problem. And what we would like to understand is, can classical machine learning algorithms do something useful in this very challenging problem? And now let's see. So in order to train classical ML algorithms, we have to feed it with some training data. That's sort of big premise of using machine learning algorithm. So here we're going to consider training data that are just a bunch of examples. There's n of them. Each one tells us that for this parameter, describing some known physical system, say some material, here is the corresponding classical representation of the ground state. And for this work, we're going to assume that we have the classical shadow. So now the theorem can be made most general, but I believe that most of these techniques also holds for other type of classical representation, like neural network representation or other things. But here, in order to prove the most general theorem, we would utilize classical shadow framework. So the training data is essentially these different high-dimensional vector and its associated classical shadow representation of the ground state. So that data can be generated by, say, a super time consuming computation, or you can also go to real world and then get some do some physical experiments to create this data. And now the goal of the machine learning algorithm is learn from this training data such that given a new parameter vector describing a new physical system that have never been generated in the real world, we want the classical ML algorithm to be able to accurately predict the ground state of this physical system. So recall that previously we looked at this proposition already. It says that assuming this well-regarded conjecture, then we cannot solve this problem efficiently, even for 2D, spectral gap 1, and so on. However, in this paper, we proved the following theorem. We showed that a classical machine learning algorithm can achieve an average prediction error of any epsilon, as long as epsilon is a small constant, using only a polynomial amount of training data and computational time. Furthermore, the classical ML algorithms work for any constant dimension, like 2D, 3D, or even 4 dimension. And for any constant spectral gap, it can predict not just one body observable, but any local observables. And it, like I said, it can achieve an average prediction error, epsilon, that's a small constant. So you can definitely go beyond 1/4, it can be like 1/10, 1/20, and so on. And all of that will remain a polynomial scalar. So essentially, this theorem shows that there exists some classical machine learning algorithm, if we properly design it, that can actually predict ground state efficiently. Oh, sorry.
So are the observables here beyond the set of observables that you would have thought the classical shadow would have
So local observables you can predict with classical shadow. So the set of observables.
The classical ML can go beyond that.
Oh no. So here the task is different from the classical shadow. So in classical shadow, there's already a physical quantum system there and has been created in the real world. And now you can measure it and then you try to learn properties. But here, what the ML model tries to do is to, given some description of the Hamiltonian of the system, it will create the ground state. So that ground state has never been created in the lab, and that's what the ML model is trying to do.
Okay.
So the class of observable is the same. But yeah.
Is this essentially equivalent to saying, okay, I did some measurements on some specific systems, and now the algorithm should predict the measurements on a system it hasn't seen before in order
Yes.
to make the shadow on that
Yes.
system and then go on?
Yes. So it looks at systems that have been created and then try to combine these information to create a shadow for a system that has.
Okay, so the classical ML algorithm is not considered a subset of classical algorithms in this case.
Yeah, so that will become clear later. I will dive into that part in a bit. So that's definitely a very valid question and a great question. We're going to talk a bit about that more formally in the later data stage.
Just to be concrete, if the system is shadowed, I'm thinking of a condensed matter system where there's a quantum phase transition or something.
Right.
You're saying you can shadow that in one before one of the parameters kicks over a phase transition. You can create these shadows and then you can predict what the property of the ground state would look like in those parameters.
That's also a great question. So I should say I'm focusing on smooth class of 2D Hamiltonians that are gapped. So that actually translated into a more physicsy language. That would mean that this class of Hamiltonians describe a phase. So you would have to train within the same phase, and then it would be able to predict other things in the same phase, but not beyond it. And that's a great question. That's also an open question. It feels like that should be impossible. Maybe you can prove that this is impossible, but there's not yet a proof that says if you only look at the one phase, and now if I ask you another phase, you can still predict it. Feels impossible to me, but maybe it's possible. So that's still open.
Sorry, don't you have to assume anything about this mapping from your physical parameters to Hamiltonians? Because the mapping is arbitrary. You can
Yeah, so that's also encoded by what I say that it's smooth. So the mapping from the vector to the Hamiltonian is not some crazy function that are fractal-ish, but it's smooth. Then it would work.
Is it sensible to ask what kind of compression the ground state is scoring? If you're doing matrix product state methods, usually those only work at 1D.
Yes.
You have a gap, but then some computation of the entanglement spectrum.
Yes.
So how is
Yeah. So how is this classical ML? That's a great question. I'll first say a few words about what this classical ML looks like, and then I'll also come back to that. So you can think of this classical ML as like a very big neural network. The input is the high dimensional vector describing the system, and then you pass through several layers, and at the end, it produces some classical representation for the ground state. So that's what we're going to essentially, you can visualize the ML model to be like that, and you're going to train these weights in the middle. But in particular in this paper, in order to prove things and understand it rigorously, we're going to take this neural network to be infinitely large. And at that point, you're going into this regime called interpolation regime, where everything becomes convex. So like usually when you have like a small neural network, when you try to train things, it would get stuck in local minimum and you cannot have analytical control for where it's going. But when you have a neural network that's huge, then suddenly you can understand its global minimum. After training on some training set, like the training set that I mentioned here, where it will go to. So that's going to be what we're going to look at here. In particular, what the ML model is going to do is essentially the following. So suppose these x1, x2, x3, x4 are the parameters in your training set. So you've seen them. You've also gotten the classical representation for its ground state, written as the sigma t of rho of x. The t just means you do like t rounds of measurements to get the classical shadow. Now, essentially, what you can prove what the classical ML algorithm is essentially doing is it will learn a function that allows us to combine these points, essentially extrapolating it and form the classical representation for this new point. So it's taking them kind of blindly and then just combining them in an extrapolation form. So that's what this is doing. And going back to the question about what is the sort of the model that's being used in performing this. So recall that while this looks like a 3D cube, it's actually a very high dimensional cube, and the volume scales exponentially in the high dimensional space. So when you only have like a polynomial number of points in the space, they're going to be very far from each other. So you really have to like, when there's like a new point, that's also going to be far from everything else. You really have to have a way that extrapolate from it. So the technique that we use in this paper is what I would think of it as like a more Fourier technique. So you try to look at the low degree Fourier modes of this high dimensional space, and you try to utilize like these data in order to do a Fourier extrapolation in order to form the new points. So that was what's being studied in this paper. There's going to be a new paper that comes out sometime after we do some more experiments where we show that this poly n can be reduced to log n. And in order to do that, what we utilize is we impose some kind of geometric locality into the ML model. So it's going to look at things in a more geometrically local fashion. It's going to look at the neighborhood and try to synthesize information from there. And using that, one can show that you can get a significant reduction in the amount of training data and computational time.
So if you can kind of view this as like you get some points and then you can predict the phase of any new point. So if you kind of think of the model as like adversarially choosing a point very close to the phase boundary, is it somehow like able to determine that phase boundary very accurately with only, as you say, log n training data? Like
yeah,
or is it just like on average the points are good?
Right. So here we're always focusing on average error. So that means it's most for most points. And furthermore, I'm like I said, I'm assuming that there's a constant spectrograph. So if you wanted to go really close, the spectrograph will start closing to the phase boundary. So that means you have to stay with it. Like I said, we don't know at the moment what would happen. Can the machine really learn well in determining the phase boundary? So that's still another question. But so here it's mostly focused on we're kind of deep in the phase, and then there's still variation inside the phase, and there are different systems, and this can predict that. So if you combine these two results, you will see something kind of strange, which is essentially we showed that for this physically relevant task, a polynomial time classical ML algorithm trained with data can predict much better than any polynomial time classical randomized algorithm, which seems kind of strange because one might thought that way classical ML algorithm shouldn't that also be a classical algorithm? What is this statement talking about? So it raises this question, which was also asked by someone earlier, that so why ML can be more useful than non-machine learning algorithm? What's actually happening? What's actually happening here? The short answer is that, like we've seen before, what the machine has to do is it can take these data and then try to extrapolate from it. So all it has to do is to generalize from the data. It doesn't really need to be able to generate those data. And the generation of those data can be very challenging. For example, you need to run some quantum computation in order to generate it. But the quantum computation is run by the physical world. So when you learn from it, you kind of inherit some of its power. And now you can utilize those data, generalize it, and to make accurate prediction. And that could be much, much easier than computing everything from scratch. So from a more complexity theoretic language or analysis, it's kind of very basic, but that was done in this paper, Power of Data, where we essentially show these complexity plots. So not really show, I mean, okay. So you can create some very contrived problems that the classical ML algorithm with data could solve efficiently, but not even quantum computation can solve efficiently. So you essentially have this kind of complexity theoretic diagram where you have, here's the problems that the classical algorithm could solve, here's the problems that quantum computation could solve, and here's the problem that classical ML algorithm trained with data could solve. So the power comes from data. So the power is not but I mean, in a sense, the power comes from data as well as your ability to learn from data. So if you just have an algorithm that doesn't learn, then you don't get this.
Just one, so now if the data is generated from real world experiments, like errors in the data, are they amplified or in this kind of learning? Or?
Yeah, that's also a great question. So a lot of the statistical, the proof of the theorem is a little bit complicated, and a lot of the complication indeed comes from showing that this error didn't screw you. So we're focusing on the situation where, like for example, of course you would have like systematic error, but you would also, even without systematic error, you still have statistical error. Like you do measurements, and that would not be correct. And essentially in the theorem, we showed that even if there's like the statistical error, and the statistical error can be as large as like order 1, but as long as it's unbiased, then the classical algorithm can still seep through all the data and make good prediction. And here's some demonstration of the numerical experiments. There's much more in the paper. Here's an example for a 2D system. It's a 2D antiferromagnetic random Heisenberg model. The high dimensional parameter corresponds to the interaction strength between every pair of spins. And we compare it with a very time intensive DMRG because we do like a snake shape and make the bond dimension quite large in order to solve for the exact values of the ground state properties. And here is the spin I and spin J 2-point correlation function between them in the ground state, and the ML prediction is shown also there. So as you can see, basically the ML prediction just gives a very accurate result by training from only 100 data points. And furthermore, the ML prediction is much, much faster because this DMRG scale like exponentially in the width, at least the algorithm, this 1D snake DMRG scale exponentially in the width of the system, but ML algorithm doesn't only scales polynomially in the system size. And using similar techniques, we can also show something, show that classical ML algorithm can be able to solve some other tasks. Another task that we look at in this paper is classifying quantum phases of matter. And basically we showed that if there exists, under the assumption that there exists some nonlinear function of few body reduced density matrices that can classify the phase, then the classical ML algorithm is guaranteed to be able to efficiently learn to classify these phases. The ML algorithm is going to construct its own classifying function that might be different from this classifying function, but one could guarantee that the classifying function that the ML algorithm finds would also be able to efficiently and accurately classify the phases. In particular, I talked to several mathematical physicists trying to understand phase transition in gap quantum systems. And as far as I know, I think it's believed that for most gap quantum systems, this assumption holds. In particular, for several known systems, say like if you wanted to classify between 1D Haldane phase and 1D trivial phase, traditionally one needs to look at string operator. They are very non-local, like span the whole system. But actually, when it's gapped, like you promise that there's a spectral gap of the system, then you only need a short string. You don't really need to have a long string. And some other examples includes you can use nonlinear functions such as topological entanglement entropy to classify between topological order phase and trivial phase. And here's another numerical experiment that we've shown in the paper. We look at a 1D system. By tuning 2 parameters, you can explore a phase diagram that looks like this. There are 3 different phases, a trivial, a SPT phase, and a Symmetry-Berkman phase. For delta equal to 0.1, that is this line, you get only 2 phases, but here you get 3 phases. And what we use is an unsupervised version of the proposed algorithm, where you don't really need to feed in any training data. You just give him a bunch of classical shadow representation for the different states at different points on this phase diagram. And this unsupervised machine learning algorithm would just figure out the phases on its own. And the result is shown in C and D. So this 2-dimensional thing that was plotted here, that's the low-dimensional representation found by the unsupervised machine learning model using what we call a shadow kernel, which is a technique that was used to proving this theorem. And yeah, so for delta equal to 0.5, there's only 2 phases, and you see that the machine learning algorithm figures there's only 2 phases by separating it into 2 parts. And the things on the boundary, like on the phase boundary, is also being placed more to the middle. And then in figure D, we consider delta equal to 3.0. That corresponds to this line. There's 3 phases, and you see that the same machine learning algorithm figures that there's 3 different phases. And this is actually expected because essentially what we showed here is that as long as there's a way to classify the different phases, then the ML algorithm with some labeled data is able to predict it accurately. And here, even without that labeled data, this unsupervised model that we're using would just try all possible classifying functions and then essentially finds one where things are the most separated. And since there always exists such a separation under our assumption, the ML algorithm is able to find it.
So maybe it might not be too surprising that we can find like the right number of phases, but how sensitive is the phase boundaries?
That's also a great question. So we tested. I mean, here we're looking at I think like 50 to 100 spins, and so the phase boundary is kind of sharp, but still not super sharp. So you can still pick a point which is kind of in the middle. And yeah, so you can, if you see here, like these points, these 2 points are already very close, and this is kind of on the middle. And then you see it can still accurately captures all of these. And for here, we also place points that are like on this boundary and so on. And you see that is still being classified accurately. So at least from the numerical experiments, it's very sensitive. I mean, it's very sensitive to where the boundary is, at least. And from the theoretical perspective, it really depends on how well this existence is. Like, I said there exists this nonlinear function, but how well can this nonlinear function classify things? If this nonlinear function can classify things pretty well, then the ML model can be guaranteed to also find that at least as well as that. So it really depends on whether there exists a function. As long as there exists, then the ML models will find the good function, essentially. So yeah, so that concludes the first part of the talk. Not sure if what time is it? Okay, I'll try to be quicker for the second part. I think the second part is also super exciting, but maybe we don't have enough time. But in the second part, we would like to understand if quantum machines can learn much faster and or predict much more accurately than classical machines. So we've seen that from these previous studies. Classical machine learning models are very powerful. It can solve very challenging tasks and so on. But we believe, as a quantum computational theorist, that quantum machines should be even more powerful in its learning ability. But when are they more powerful? So this is going to cover these set of papers. And we're going to distinguish between the following 2 settings. The first is the classical agent. So this is just a more personified term for classical machines, where the classical agent can receive, process, and store classical information. On the other hand, we would have quantum agent, which are agents or machines that can receive, process, and store quantum information. So I don't think we yet have this technology there. So first, we were thinking about it as there's some quantum sensor that can receive quantum information from the real world, store that quantum information in a quantum memory, and then process it using quantum computation. I think that whole pipeline is not yet there, but I think people are here as well are working hard on realizing such a technology. And the key question we would like to understand is, what are the advantages of a quantum agent over a classical agent in learning about our physical world? And this is not just important for, say, the field of quantum machine learning, but more broadly, because understanding such a question can allow us to understand whether future quantum technology can fundamentally alter our ability to learn about the universe and to do science. In particular, in this, just try to give some very simple example showing that there's a huge separation between their learning ability. Particularly, let's focus on a very simple situation. Assume that the only thing that's unknown in the entire universe is some n-qubit state, and the classical agent can perform measurements on each state in each experiment to get classical information. But a quantum agent can utilize its powerful quantum sensor to obtain a copy of the state coherently from each experiment. And we would like to understand, given these two dichotomies between classical and quantum agents, what can we do? What kind of things can a quantum agent do that a classical agent cannot? Particular in this paper, we proved the following exponential separation for the task of predicting Pauli observables. So in this task, the classical and quantum agent would learn about this unknown n-qubit state by doing multiple rounds of experiments. For the classical agent, each round involves a measurement, get a data, and then do another measurement, potentially different, and then so on. A quantum agent can just store these quantum information in the quantum memory and perform some entangled quantum data analysis on all of them. And subsequently, the quantum agent would like to say predict the expectation value of these Pauli observables for all Pauli observables, so all 4 to the n of them. And the paper, we proved the following theorem. We showed that a classical agent would require at least 2 to the n experiments just to predict one adversarially chosen Pauli observable. So it does the experiment, and now some adversary comes and then say, hey, predict this Pauli, and it will not be able to accurately predict it if it do less than 2 to the n experiments. But a quantum agent only requires a linear number of experiments, and then using that, it can predict all 4 to the n observables. And these exponential separation is present even when the state rho is a classical distribution over product state. So there's no entanglement. Even in that situation, we can still show this exponential separation. And the key idea behind this theorem is that uncertainty principle, some strong form of uncertainty principle, which significantly limits the learning ability of classical agent. Think of it as if you wanted to get position and momentum both correctly, you would have to do at least 2 experiments. And here there's a large number of observables that are anti-commuting with one another. So if you wanted to learn about all of them, you have to do an exponential number of experiments. On the other hand, which is quite surprising, quantum agent doesn't suffer from uncertainty principle in the same way the classical agent would do. By storing these copies in its quantum memory and doing some entangled measurements across all of them, it can actually extract all of these incompatible observables in a very fast fashion. And these kind of separation holds in many, many different tasks. After we have developed this mathematical framework for proving advantage. We showed that if you wanted to perform quantum PCA, you get exponential advantage. If you wanted to uncover symmetry structure in dynamics, so you wanted to distinguish if some unknown dynamics satisfy time reversal symmetry or not, you also get exponential separation. If you wanted to learn some unknown physical dynamics generated by some polynomial time quantum process, we can also prove that you get exponential quantum advantage. And all of these is done using a very learning theoretic technique. Basically, this is a collaboration with 2 classical learning theorists. They propose in classical world, they have all these nice tools to understand the limitations of learning, and we're essentially employing them in order to understand these quantum advantages. So due to the time constraint, just wanted to say, in 2 papers, one a theoretical paper, we showed that these advantages, these very large advantages, still persist in noisy quantum computers, and we have done an experiment with the Google team. So in particular, we've done an experiment with on the Sycamore processor, utilizing a total of 40 qubits, and show that you can already see within this kind of noisy setting, a large advantage for using a quantum strategy for learning about physical system. And here's another demonstration for learning physical dynamics. In particular, we're trying to have this ML model discover the underlying symmetry structure of the dynamics. And we saw that the quantum agent can find that very efficiently, but a classical agent would fail, as expected by our theoretical analysis. So to conclude, essentially in this work, I presented several recent progress on understanding how to efficiently learn in the quantum universe using either a classical machine or a quantum machine. However, in my personal view, I feel like most of our existing results has focused on more fundamental and more basic, or you could also say lower level tasks, such as predicting properties, classifying phases, predicting ground states, and so on. But in the coming years, what I really hope to see is to have a better understanding on creating rigorous machine learning algorithms for even higher level tasks, such as designing quantum circuits to do useful things, designing quantum protocols for communications, designing quantum algorithms that have advantage over classical algorithms, or even more ambitiously design, create ML algorithms that can discover new physics. So finally, I wanted to say a few more words about the long-term ambitions of this research program. Particularly, there are 2 points. The first, I think, is more direct. Basically, we wanted to develop our understanding of learning to a point that we can really use it to accelerate and automate scientific development. And perhaps one day when we really have advanced learning theory to a sufficient point, it might give rise to an algorithmic theory of science, meaning that you can just write down a code and you understand that code very well. And then if you just keep running that code, it would discover everything we need to discover about our universe. That's very ambitious. The second ambition, I think, is probably also shared by many people in sitting here, is we wanted to build a quantum machine. Okay, this part maybe not, but we wanted to build a quantum machine that can allow us to understand more about our universe. But I wanted to take it a bit further. We wanted to build a quantum machine that's capable of learning on its own and discovering new facets of our universe beyond the combination of humans and classical machines. And here is some figures that AI generated on its own, imagining that itself is learning and discovering about quantum. That's it for my talk. Thank you so much for listening.
Yeah, we have time for a few questions.
Yeah, so love the talk, thanks. On the stuff you went through in the last 10 minutes.
Yes.
You were comparing the classical to quantum approach, and I'm wondering how generic your classical approach was. So, for example, does your classical approach allow subsequent experiments to be conditioned on results of previous experiments?
Yes. So that's actually one of the, I would say, the most hardest technical part of these proofs. Like there's been previous work trying to understand the setting where you just have what people call independent measurements. So it's like you already set up what are these measurements and then you do them. But the most powerful scheme would be the classical agent can first do some experiments based on that results, adapt itself, and then do the next one. And here all these proofs consider this situation. That is, you can have arbitrary adaptive procedure for the classical agent, and yet it would still require an exponential number of experiments.
So in this setting, a classical agent needs this exponential number of experiments. You get this exponential speed up from a quantum learning agent, right? But in the previous setting that you talked about with like the 2D phase thing, you have this classical learning algorithm using polynomial time measurements. So like, what's the difference between these two settings?
You mean this one or the predicting properties one?
Yeah, this theorem exactly, right?
Yes.
The ML algorithm now needs polynomial, but in this case where I'm predicting PAULI,
Yes.
gates, it needs exponential.
Yes. So basically what's happening here is, I think it would go even further back to what I talked about earlier for classical shadow formalism. So like when you use this procedure, it's a very classical procedure. You just do measurements and then classical data, you can only predict local observables. And you can also predict some global observables, but they have bounded Frobenius norm, meaning that if you write down the observable, trace of O squared should be bounded by some polynomial number. And Pauli observables has a Frobenius norm that scales exponentially in system size. So essentially, Pauli observables lie outside of what classical shadow could do. And for example, if you look at here, this result focuses on predicting local observables. The Pauli observables, if you think of it as the tensor product of a high weight Pauli, then that's not local. That's a very high weight string operator. And that's when things become very hard for classical machine learning algorithms. You need the quantum enhancements in order to learn these highly incompatible Pauli things.
Yeah, I had a question about this sort of complexity diagram.
Yes.
Where you have the classical algorithm trained with quantum data. And
Yes.
EQP.
Yes.
So what would be an example of something that might be easier with a classical algorithm or like outside EQP, but accessible for the classical algorithm?
Yeah, that's also a great question. So actually, one way to think about data is you can think about it as an advice string in complexity theory. So advice string is something more powerful than data. Advice string is essentially some advice from some all-powerful being that try to maximally improve your ability to do compute. And data is a more restricted version of that. Data is just a bunch of examples for this input, what's the corresponding output. And essentially, it's well known that advice, like the advice class, also known as P/Pauli, contains things that are outside of EQP. Because you can think of the advice that's being provided to the classical algorithm to be like say outside of RE, so like undecidable advice. Then in that case, you can show that it would be so powerful that it's outside of not just BQP, but like QMA and entire class of RE. This is a similar thing that happens here. If you formally analyze it, if the data itself is undecidable, then it will be able to solve undecidable problems. That was an example that was given, but that's super contrived because we don't expect to get undecidable data. That's just unconceivable. What I would usually imagine is this data would come from at most like the physical world, and if we believe that the physical world can be simulated by quantum computation, then this data is the most as powerful as this. So this class should also lie inside quantum computation.
About your quantum learning approach, you said that like ON, like quantum experiment suffices to learn, like you can predict all the forward-leaning observables at the same time.
Yes. I guess you wanted to understand a bit more like what's this quantum learning algorithm. So yeah, I could say a few more words about that. So the quantum learning algorithm has two parts. The first part is it performs two copy measurements. So it essentially stores row and then another row in its quantum memory. And then it performs Bell basis measurements on each qubit. And you just repeat that for order n times. Now you would get a classical data. And essentially one could show that using that classical data, you can predict the absolute value of this expectation value. And then the next thing you need is to predict the sign in order to get this. So now in order to predict the sign, what you should do is what the quantum agent essentially does is it would keep a bunch of copies of the state in its quantum memory, and then it would only look at things with large magnitude, like the absolute value, like sufficiently far from zero. In that case, you can show that majority vote would give you the sign with almost certainty. So now the quantum agent will just keep measuring this uncopy thing and uses gentle measurement lemma to show that it wouldn't affect that system too much. So the quantum agent can extract all the signs.
So for this Pauli prediction problem, you have shown there's a quantum advantage in predicting for quantum problems. But is there also advantage for application of quantum learning algorithm for classical problems?
Yeah, that's also a great question. So I've been thinking about that quite a while. It is very challenging. At the moment, we only have super contrived examples, like some task that never appears in practice at all. And then we can show some exponential or super polynomial advantage in those tasks. But at the moment, I don't think, I feel like, for example, this one is like more physically relevant and more practical, but like the one for completely classical problems, we don't really have any at the moment. So that's definitely also a problem that we should, like, but I mean, there's like polynomial advantage, but not exponential.
But I'm just imagining, so this is like this is like quantum Hardy predictions, but for example, we have like a classical Ising model, anyone down similar problems using quantum algorithm.
I see. I don't really, I don't think there's any works on that yet. So that could definitely be an interesting venue to explore. Like suppose it's still like a physical system, very similar to quantum, but like complete classical. Can we get things there? At the moment, I don't really know, but I think that's a very interesting future direction.
So as we're short on time, I suggest we move the rest of the questions offline. So let's thank our speaker once again. That is